Hello, ladies and gents. We are going to be taking a look at intermolecular forces, states of matter, and solutions, and how all those are related to each other. So recently, we just took a look at Lewis structures and molecular geometry, and just as a brief review of how to do that, the first thing you would do is draw the Lewis structure based on the formula that you're given. And make sure, of course, that you come up with the most reasonable structure by checking the formal charges on all of the atoms in the structure that you've drawn. From that structure, you'd use the number of clouds of electrons around the central atom to determine the molecular geometry. And with the molecular geometry and the bond polarity, you'd be able to use the combination of those two to determine the molecular polarity. Once you have the molecular polarity, that's when we can start taking a look at how that molecule will interact with other molecules, including other molecules of its own type. So hopefully by the end of the review of the structures that you have done, you should be able to determine if a molecule is polar and whether the positive and where the positive and negative dipoles are at. Intermolecular forces is the attraction of two separate molecules for each other. And those could be two separate atoms that have an attraction for each other as well. And if you're specifically the picture that you're currently looking at is one of a polar molecule being attracted to another polar molecule by looking at the molecular dipoles that are there. There are two major types of intermolecular forces. There are dipole-dipole forces, where polar molecules are attracted to other polar molecules. And there are dispersion forces. And in general, this is the attraction between non-polar molecules. Now, this is a bad definition. This is not the final definition we're going to use. There's a better one coming. But in general, there is two types of intermolecular forces, one for polar molecules and one for non-polar molecules. Dipole-dipole attractions are where you have separate dipoles, or the positive and negative dipoles within a molecule, and you have a positive dipole attracted to a negative dipole. Now, taking a look at the structure of hydrochloric acid, if you notice there is the HCl, so you drew the Lewis structure, and if we were to draw the Lewis structure like we had done in the past, you would figure out the number of valence electrons you have to work with. You would determine that the chlorine in this particular case, or the hydrogen at this point, really doesn't matter since there's only two atoms, one of those being the central atom. The number of valence electrons around the chlorine is 8 valence electrons if you include the single bond. Once you have that established, you can then draw that the polar bond for the chlorine is going, or the polar bond between the hydrogen and chlorine will give a negative dipole around the chlorine and a positive dipole around the hydrogen. So if you had a second molecule of HCl, then the positive dipole of the hydrogen would now be attracted to the negative dipole of a different molecule to the chlorine end. With all that put into place, you'll notice that there is the structure that's here that's a dashed line. So I want to make clear that this solid line is a very, very, very strong covalent bond. So this is an actual covalent bond holding that molecule together. The dashed line, all the dashed line is an attraction. This is not necessarily a strong attraction, or at least not nearly as strong as a covalent bond would have. However, this intermolecular force of attraction does allow hydrogen chloride hydrogen chloride molecules to be attracted to other hydrogen chloride molecules. And the same thing will be true for the hydrogen sulfide. So you'll notice these dashed lines are the intermolecular forces, while the solid connected lines are the covalent bonds. So again, the intermolecular forces are not nearly as strong as the covalent bonds will be, but those attractions are still there and do make a significant difference on how molecules interact with each other. So the dipole-dipole attractions, again, are the negative dipole of one molecule being attracted to a positive dipole of another. Those attractions could also happen between two separate dipole molecules or polar molecules. So for example, if we were to combine these two with each other, the hydrogen of the HCl would be attracted to the sulfur in the hydrogen sulfide. So there are certain dipole attractions that are extremely strong, and these will occur between a molecule that has a nitrogen, oxygen, and fluorine of one molecule, and it is attracted to the other molecule that has a hydrogen that is covalently bonded to another nitrogen, oxygen, or fluorine. And this is called a hydrogen bond. That hydrogen bond is not a covalent bond. This is still an intermolecular attraction. And at best, this hydrogen bond is about 5% of what a covalent bond would be. But it is an extremely strong dipole-dipole attraction. So it is still a weak force, but it is considered one of the strongest intermolecular forces. So let's take a look at the definition of what that means. So here you will notice on the water molecule on the left that you have an oxygen. Oxygen, nitrogen, and fluorine are the three most electronegative elements on the periodic table. When the nitrogen, oxygen, or fluorine of one molecule has a negative dipole and is attracted to the hydrogen of another molecule, but that hydrogen does need to be attached to one of those extremely electronegative substances as well. So this portion over here that the hydrogen's attached to needs to be either N, O, or F. So while it sounds like a very complicated definition, if you have a picture to look at, the picture is going to be make it quite easier to figure this out. So a hydrogen bond is, well, you're starting off with N, O, or F on one molecule, and then you're looking to see that it's attracted to a hydrogen, but that hydrogen needs to be covalently bonded to also an N, O, or F to make sure that this bond is remarkably polar, to make sure that this intermolecular force is going to be very strong. So this here is the hydrogen bond. Hydrogen bonds have examples that occur in DNA chains. So I'm sure you have heard of DNA, and in biology you've heard that the two sides of the DNA will match up, G with C, A with T, etc. And why do those things plug in together, and why do they not match up with other substances? Well, if you notice, here's the adenine and here's the thymine. And with the thymine, you'll notice that you have the oxygen, and there is an attraction to a hydrogen in the adenine, but that hydrogen is specifically attached to the nitrogen. So this is a hydrogen bond. Same thing is occurring with the other one, but this time you'll notice that the nitrogen is on the adenine, and the hydrogen it's attached to is on the thiamine, but still the thiamine, again, the hydrogen is attached to nitrogen on the other side. So you'll notice that there are exactly two connections at a particular distance and angle that can occur between the adenine and thiamine. And you'll notice there are three when it comes to guanine and cytosine. In the cytosine, you have an oxygen, and again, it's attached to the hydrogen. That hydrogen is attached to the nitrogen. The nitrogen is the more electronegative, and so therefore you're able to make a hydrogen bond between those two. And you'll notice that there's three hydrogen bonds that occur between the cytosine and the guanine. So you'll notice, by the way, that without this particular type of intermolecular attraction, the ability for DNA to even exist would not be there. Those connections are what allows those backbones to connect with each other. So I'll give you an opportunity to try this on your own. What you should do is take a moment and determine whether or not these molecules would have hydrogen bonds or dipole-dipole attractions, or would those not have either one of those? So you actually do have three options. Do they have hydrogen bonds? Do they have dipole-dipole attractions, or neither? Give you a moment to work on that. So So taking a look, hydrogen iodide would be a dipole-dipole attraction. If you drew out the Lewis structure, you would find that it was a linear molecule that ends up that has just a binary connection, just hydrogen to iodine directly, making a negative dipole around the iodine. Between the nitrogen and hydrogen in ammonia, you would have a hydrogen bond between one ammonia to another ammonia molecule. So some people would say, if you take a look at the CH3F, might think that that would have had a hydrogen attraction. However, if you were to look at the overall structure, while you have the fluorine able to form the dipole, the strong negative dipole, the hydrogens, on the other hand, on this molecule, are not attached covalently to a N, O, or F. So if I had a second fluorine, or let's say a fluorine that's over here, that's attached to a different molecule, and I won't draw the rest of it, this attraction here would be a dipole-dipole attraction. However, since this hydrogen is not attached to a fluorine, or an oxygen, or a nitrogen, that would make this just a dipole-dipole attraction. It's still going to be a strong dipole-dipole attraction, but it will not be a hydrogen bond. CF4 is neither dipole-dipole nor hydrogen bond, since it is a non-polar molecule. As we're looking at the CH2HF, let me try that again. CH2F2, it is a dipole attraction, very similar reason to the CH3F that we looked at a moment ago, but it is a polar molecule. The HF will be hydrogen bonds. The CH2O is going to be dipole-dipole, so there should be a double bond attaching the oxygen to the carbon. And carbon dioxide is going to be also neither, where it's not going to have hydrogen bonding or dipole-dipole attractions. It'll have dispersion forces only. And so that hopefully leads us right into what is a dispersion attraction. So the dispersion attraction, non-polar molecules form a dispersion attraction. With this particular diagram, what you have is a nucleus centers and then these gray electron clouds. So what happens when one molecule, or one of those atoms, or it could be a molecule, moves closer to another one, the electron cloud of one of those atoms will start to disturb the electron cloud of the other, shifting it in its shape, creating temporary or induced dipoles. Those temporary dipoles will cause an attraction, and you'll get this vibration that goes back and forth. So you'll notice that there's going to be this constant shift and ebbing and flowing, almost like an amoeba going back and forth, that causes these temporary dipoles for the attraction to take place. The larger an atom or molecule is, even if it's nonpolar, the larger it is, the more opportunity there is for polarizability. So the ability for those electrons to shift to one side of the molecule or another, creating a stronger attraction. So every molecule and every type of substance will have some type of dispersion forces, because there's the ability for those electrons to shift randomly and create those induced dipoles. So non-polar molecules will only have dispersion attractions, while polar molecules will have their dipole-dipole as well as dispersion attractions. Once again, special polar molecules will have hydrogen bonds as well as dispersion forces as well. So those dispersion forces can happen with all molecules and atoms. So this is granted a pixelated version of a diagram. However, this is the general trend for strengths of these intermolecular forces. You'll notice that ion dipole happens between an ionic ion and a dipole molecule. We'll talk about those in general. So far, we've just referred to them in a homogeneous sense. But as the dispersion forces, which by the way are also called London forces, those are generally the weakest variety of intermolecular forces. Then you have a dipole-induced dipole, an ion-induced dipole, dipole-dipole attractions, hydrogen bonds, etc. But these are generally currently in order of strength. However, if a question like this is asked of which of these will have a stronger intermolecular force, chances are you'll be provided with data in the form of either melting points or force of attraction or some type of other information that'll give you the idea of which one has the stronger intermolecular force. So you do need to refer to the data. While this is a general trend, if data is given, the data is going to be more powerful than just this general trend. Make sure you're using whatever information is provided to you in the question that you are given. So with the intermolecular forces and solubility can be explained now by the intermolecular forces. So solubility and intermolecular forces, well, why does salt dissolve in water? Why does ethanol dissolve in water? Why does oil not dissolve in water? And we'll talk about miscible versus immiscible liquids. And what does soap do? So how does soap have the ability to remove oil off of skin or grease off of skin? So we have discussed the idea of salt dissolving in water before, and what you're forming in this case is a ion dipole attraction when water dissolves when salt dissolves into water. So in this very first picture, you'll notice the salt is being combined with water, and it's just a pile. It has not had an opportunity to start dissolving yet. So then what you have is, of course, Mickey Mouse's head, and pardon me for the bad drawing, but if you got the water molecule, you'll have your positive dipoles around the ears of Mickey Mouse's head, and the negative dipole around the neck of the water or the oxygen portion. So if you were to then combine that with the ionic salt crystal, sodium chloride ions are going to start to have an attraction for each other, which holds the crystal together. So you have this attraction within the formula units of the salt, and then the water will be attracted to those components. So for example, the chloride ions are the green, so those will be negative. The negative chloride ions will be attracted to the oxygen end of water, while the positive ions will be attracted to the, the negative ions will be attracted to the positive end of water. So you'd have the separation of the attractions, or the separation of the salt due to the attractions of the water for the ionic crystal. The reason that salt dissolves in water is because water has a stronger attraction for the ions than the ions have for each other. If the ions have a stronger attraction for each other than the water has for the ions, then that salt will not dissolve in water very well, which then gets us into insolubility, and eventually we'll get into the partial solubility of those substances with KSP and equilibrium problems of insoluble salts. So, but in this particular case of looking at just salt and water, the water has the ability to pull the formula units apart of the salt crystal, surrounding the ions, and separating from each other. And when the substance is completely dissolved, you have the ions completely surrounded by water molecules. So why does ethanol dissolve in water? Well, so what we're going to do is have you take a look at drawing the Lewis structures for both ethanol and water, and then you should try to see whether or not you can determine the type of intermolecular attraction that water and ethanol will have for each other. Take a moment to do that. So the structure on the left is ethanol. And with the structure on the left, you'll notice that you can form hydrogen bonds here. As a matter of fact, that while they drew in this particular diagram just one hydrogen bond, you can potentially have a second one that occurs here as well. So the oxygen attracting to this hydrogen, and this hydrogen is, by the way, within the molecule covalently bonded to NO or F. Once again, the N, O, and F are those three most electronegative elements on the periodic table, and that's what you're going to be looking for. Granted, this is a dipole-dipole attraction, and that dipole-dipole attraction is so strong it's a hydrogen bond. The way that water dissolves so many items is that it's attracted to ions, and it's attracted to dipole molecules. So polar molecules are very soluble in water. If you have a liquid that is soluble in water, like ethanol, the term is referred to as miscible. Miscible liquids are where two liquids will combine and blend together. So ethanol and water are miscible. Methanol and water would be miscible. Methanol, by the way, is the most common liquid component of windshield wiper fluid. So what about soap? Let's get to soap later. Why does oil not dissolve in water? Oil does not dissolve in water because it only has dispersion attractions and does not have any polar end to it. So oil will be these long structures of carbon chains, not having any polarity to that molecule in the slightest. So while you will have dispersion attractions that will keep the oil molecules attracted to each other, there's going to be very little to no attraction between the oil and the water itself. So when you have non-polar molecules and polar molecules together, they will not be attracted to each other. So there is a common phrase that you may have heard of before, whereas like dissolves like. So polar will dissolve in polar, non-polar will dissolve in non-polar. So in this particular case of water being combined with oil, that the oil and fats have long non-polar chains, and when they are poured together, they don't combine because there's no molecular attraction or very little molecular attraction between them. So then how, at this point, do you get soap to work? Well, soap as a general structure has a long non-polar tail. So it is a molecule of long carbon chains that is non-polar, but then at the very end of it, there is a head to that molecule that has a polar end to it. And by the way, for those people who are noticing, you'll notice that there is the potential for resonance in this structure as well. So that double bond and this negative charge would be able to flop back and forth, where the negative charge would turn into the double bond, and then the double bond would turn into the unshared pair of electrons on the oxygen, forming the negative formal charge. So yes, there's some resonance at the end of this, but it is definitely very, very polar on this end. And granted, soap would then also require a positive ion to match with that. And so let's just say that on this end, you would have sodium with a positive charge. So now you have an ionic attraction between this end, and this would then be your overall molecule and or ion of soap. When you put that into water, the water portion that will dissolve is this end over here. So the sodium ions would get pulled away by water molecules, specifically the oxygen end of the water molecule, and the polar head of the soap portion would be attracted to the hydrogen end of waters, and you'd be able to get that to be separated. When you put that into oil, on the other hand, the non-polar end over here would be attracted to the oil. And so you would get that long non-polar tail dissolving in the grease or oil. So how does that all work then? Well, if you have an oil, oil and water, and you're trying to get those to mix, the non-polar ends would be sticking into the oil, the polar ends would be sticking into the water, and you would have now a combination where it is dissolving in both of them at the same time. These are called emulsifiers. Now those emulsifiers have, again, a polar head, which is hydrophilic, which means that it's attracted to water, and then the long non-polar tail is called hydrophobic, where it's not attracted to the water. So the way that you would get oil droplets to be suspended into water is by using an emulsifier. So you can dissolve it into both, where you have soaps, and examples of some emulsifiers are soaps, egg, mustard, and lecithin. Lecithin, by the way, is a common ingredient that is added as a food additive. It does come from natural sources like soy, but you could use egg or mustard as an emulsifier as well from a food source. So the way that soap would work if you have grease or oil on your hand is by adding soap, you dissolve some of the oil into the soap end of it, and then the soap, the polar head of the soap would be able to dissolve in water and get washed away. Which, by the way, is why soap can kill COVID. You don't need a lot of soap to be able to kill COVID, but what you need is the ability to dissolve some fat. So how does that work? Well, this red layer that is here, or that is here, that red layer of the coronavirus outside edge is made of fat. So that envelope is a fat-based substance. All you need to do is be able to dissolve some of that fat-based substance. And once you dissolve that fat substance, this will break open, springing open the RNA, making it generally unusable and killing it off. So the spike protein is not going to be able to do its job and basically just killing the virus. This is more effective than ethanol. While ethanol will do the trick, because ethanol is partially soluble in fat and partially soluble and definitely very soluble in water, soap does a better job because it actually emulsifies the fat layer that is holding the coronavirus itself together. So yeah, as a reminder, please wash your hands. All right, so this is going to be the end of part 1. And we will revisit this as well, or we'll review some of this as well in the next session. With any luck, this gives you a good foundation to start with what intermolecular forces are all about.